Okay, so this is kind of your little mini lesson. This is available in the teacher section as a video. So, this video right now is just to kind of walk you through the science behind insulators and conductors. There is a video that I put on your grid that can go through this, and the little guy that's in the corner there, he'll talk you through it. However, I know some of you would rather have me explain it because I kind of obviously do things in a different weird way. So here you go. Here is his first screenshot. All right. So when they talk about conductivity, right? Think of our terms when we talked about convection, conduction, and radiation. Conduction. With conduction, there's touching, right? So if something is a good conductor, that means that their molecules need to be touching, right? So in order for heat to pass through, or that thermal energy to pass through an object, right? Those molecules need to be super close together. So that way, if they're spazzing out and moving really fast because they're hot, they can easily bump into the next molecule, which can easily bump into the next molecule, and it passes, kind of like a domino effect, right? They're close together, so it's easy to touch the next molecule over. So with conduction, there's touching. You need to have those molecules touching. So if you look down at the bottom here, it says conductors are usually made of particles. You could also think of molecules that are close together, neatly organized, right? So when you're thinking of those metal objects, those metal pots and pans, those have molecules that are close together. And that's the whole reason why, as soon as you turn on the stove, it starts to warm up your pot or your pan, which then transfers over into your food quickly. Okay. When you're talking about an insulator, it's so weird because you would think an insulator, because, ooh, that warm little coat that wraps around you, it must be really dense because that's what keeps you warm. It's actually the opposite. So if you look at the picture here of the molecules, right? Insulators are made up of particles that are far apart. They're disorganized, right? Look at all these little air pockets here. Yeah? See the air pockets? Cool, cool, cool. So the reason why this is a good insulator is because if you think about it, on one side of your coat, if it is super, super cold out, right? And then on the inside of your coat, you're like nice and toasty and warm, right? You don't want that heat from your body to bump into the molecules on your coat, which can then bump into the air molecules. And then basically that's the heat energy leaving you, right? And you would feel colder. You don't want that transfer from your body to your coat to the air around you, right? So you have to take out that chain reaction. And by taking out the molecules, making fewer molecules, spreading them apart, having those air pockets in there, that's how you end up with that chain reaction being broken, right? So picture those dominoes, right? You push over some dominoes and then they just fall flat because there's not another one there to push. Okay. So that's the whole reason why your air is trapped inside your coat, right? Your heat molecules are bouncing around, but once they hit your coat, they're not constantly bumping into the next round of molecules, right? They still hit them, right? You still leave a little bit of energy into your coat, and that's why you get a little bit cool, right? But so anyway, that's what you're looking for. So it's almost the exact opposite of what you would think. If something's going to insulate you and keep you nice and toasty and warm, it's actually going to have less density in the molecules, right? They're spread out. Cool? Okay. So the next thing that I wanted to go over with you would be just some of the other screenshots, right? So they're saying anything with empty space, right? Empty space is a good insulator, right? So your jackets, right? The reason why a down jacket filled with all of these little feathers, those little fluffy, nice, expensive coats, right? The reason why those work so well instead of like a hoodie that is like really thick material, you would think that the hoodie would keep you warmer, right? Well, it's all of those little pockets of air inside your jacket that keep the heat from leaving your body, right? Because there's nothing to bounce into. Those molecules are not as dense, right? So it's not an automatic transfer of heat from your body to your coat to the outside air. When the heat from your body, those molecules bump into the molecules inside your coat, there's fewer dominoes you could think of to bump into. So that like reaction is a little less extreme. Okay. Same thing with a thermos. Okay. So if you've watched any of these videos, that's the whole purpose of a thermos. You have an inside layer and an outside layer, right? So that vacuum that's going on in between your layers is empty space, right? They literally take out the molecules within that layer. So when things are bouncing around inside, if this is like really, really warm liquid, right? And everything's spazzing out, when it bounces up against the layer of a vacuum seal, there's no molecules there. So think about that. There's no energy being transferred. It's all staying inside because it's not touching something else that's slowing it down. Okay. That heat, that energy gets to stay right there. Okay. If there were molecules there, it would bounce into those, which would then bounce into the next. And then that's how it ends up trailing out of your cup. Right. Okay. So that is kind of your wonderful explanation. So if you think of this nice fluffy insulation for your home, there's actually pockets of air within your insulation, and the density of your molecules is it's less dense, right? So that domino effect is not happening as quickly. So all of the energy within your home gets to stay in there. It's barely hitting up against things within the insulation, so it's not really leaving your house. Okay, so you're looking for the air pockets. It's kind of why styrofoam works so well. Think about all the air pockets that could pop into your styrofoam. And then this is just like a scientific table with information. Not that you really need to know what all the numbers mean, but I do like the fact that it points out the fact that the higher a conductivity level, the better it is as a conductor. It's basically the higher the number, the more packed the molecules are, right? So the more bouncing around that can happen and the quicker the heat can transfer through it. So that's just kind of another way to think about it. How many molecules are packed into that space? So your pots and your pans are good conductors. So they're packed in there, and that energy can transfer through one molecule to the next really quickly. And that is it.